Good morning, everyone. Couple announcements first. I'll be holding for my section really a Q&A/review session on Wednesday, May 8th from 9 to 11 and 1:55 Grinnell. Okay? And there won't be any office hours that week because of this 2-hour section. And I'll be sending you guys out some practice questions next week, and we'll use that as the basis of our question answering period. And for those of you weblanders out there that have been watching this lectures on online as opposed to here, this is not recorded in Grinnell, so you'll actually have to show up if you want to partake. Okay? And for those of you listening to these lectures for the first time on May 9th, the review session's over, so keep that in mind. I think if I was in college, if I had all this online stuff when I was in college, I'd definitely be looking to do stuff at the last moment, but we're not going to tell anybody about that. Today we're going to do directional cues, finish up development, do inductive signals, questions on you should look at page 66 in the reader. Then we'll start in on a system overview very briefly, and then we're going to do our system flyby. Can't do physiology justice in 4 lectures or so, but we'll give it a try. And we're going to then hit digestion, hormones of digestion, and if we get that far, absorption, and then there's questions. And also, Mike wanted me to remind you guys that the final is Monday, May 13th, 8 to 11 in Haas Pavilion. And I think you guys have gotten other information on that. And we'll continue to be flooded with information so that you know that it's May 13th, 8 to 11. Okay? Any questions? All right. Just a very brief review of what we talked about Wednesday. We talked about stem cells. Stem cells self-renewal or they differentiate. The idea is to try to figure out what's the differentiation signals for a specific cell type. Different kinds of stem cells know the difference in the sense of what's a totipotent stem cell, which is can form all tissues, embryonic and extra-embryonic. We talked about pluripotent stem cells. The most important ones of this group would be the embryonic stem cells, or ES cells, which come from the inner cell mass. Then there's also embryonic germ cells, embryonic carcinoma cells, or other sources of it. But it's the inner cell mass where most of the attention is being played in the field right now. Then there's multipotent and unipotent stem cells, which are basically most of the adult stem cells. There's a restricted differentiation, and this is also cancer stem cells fall under this category. And a lot of people are playing with this because they're accessible in adults. Adults obviously have them, you get less of them. But the idea behind that actually is if you're an adult and you need some new tissue, if you pull out your own stem cells, you don't have to worry about immunorejections and things like that because they're your own cells. So there's a lot of attention being played to that. Then we briefly mentioned that in vitro you can fertilize, go to blastocysts, take out the inner cell mass, and then do in vitro manipulation. A big chunk of the research going on tries to figure out how to do this, how to manipulate these stem cells in vitro. We also talked about somatic cell nuclear transfer, where you take out a nucleus of, say, an oocyte, put back a diploid nucleus, and look for differentiation. Has a lot of potential. The one downside of that technique is that there's a possibility of aneuploids, getting extra chromosomes, and that has not been particularly worked out yet. And then also talk about reprogramming differentiated cells to ES-like cells. And this works in mouse cells, and some other species. I don't think it's been tried that successfully in humans yet, but you can take a mouse skin cell, reprogram it to become an ES-like cell. So that would be a way of generating lots of stem cells. Okay? Then we talked about continual development. Obviously, stem cells exploit the differentiation profiles because of where you can get where the cells from. Then we got into gastrulation, which you form a 3-layered embryo: ectoderm, endoderm, mesoderm. And in humans and also birds, you have a primitive streak, which is where the cells involute inward to form, and where the cells end up dictate whether they're ectoderm, endoderm, or mesoderm. We talked about that the trophoblast becomes the chorion, which surrounds the embryo. It's an extra embryonic tissue. The hypoblast is also extra embryonic, forms a yolk sac. Humans, yolk sac-like structure, but humans don't have yolk, and then produce early red blood cell formation. Then we talked about how the epiblast of various steps becomes the ectoderm, endoderm, and mesoderm. And you should have a sense of that. Any questions on gastrulation or stem cells, actually? Okay, and then we ended with organogenesis. I forgot to mention that the layer that the cell wedging comes from in the example that I gave you, which is forming the neural tube, is from the ectoderm. So the ectoderm cells wedge. They change shape and pushes out the cells, part of the cell layer, eventually blebs off of it or comes off of it, and you get a neural tube. The cells in between, what's left of the ectoderm and the neural tube, are called the neural crest cells, and those actually migrate and become bone cells. And then we talked about convergent extension. I called it convergent cell extension. Same thing. Convergent extension is a term. It's for morphogenesis, which is the shape of an organism. And basically, it's one mechanism where cells can come together, interdigitate with each other, and you get a new row of cells that is now longer than the original rows. So it's a way you can change shape strictly by cell movement. And that's an important feature here. It's cell movement changes it. Cells aren't dividing out, but they're actually moving. Okay? And there's multiple mechanisms. These are just 2 of fairly well-studied mechanisms. Any questions on that? Okay. Oh, question up here. Say it loud. I'm not sure the answer to that question. I'll look it up. Yeah, I'm not sure about it. Yes?
So the primitive streak forms the endoderm, mesoderm, and the primitive ectoderm?
Yes, what happens, I left that out, I talked about it. The epiblast eventually becomes the primitive ectoderm, and then off of that becomes the primitive streak, and then the primitive ectoderm forms the ectoderm, i.e. the name primitive ectoderm, and the primitive streak, when the cells involute, become the mesoderm and the endoderm. Right. Okay. Then one last little bit of this is the fact that the cells move, and you have something called directional cues. And this classroom is actually a good example of directional cues. And that is, you have a cell, and it wants to move down to here. The straight distance, the shortest distance might be from here to here, right, this diagonal, but the cell itself actually moves like this. It has a series of positive directional cues to keep it online, and a series of negative cues to keep it from straying. And this classroom is a good example of that. So you guys in the middle of the classroom, you came down and sit. Why didn't you just come in and walk over the tops of the chairs where you're sitting? It's the shorter distance, right? The shorter distance in the diagonal. The answer is you have negative and positive cues. The positive cue is a nice hallway that comes down, the space in between the chairs. The negative cue is the possibility of falling and stumbling as you walk down on top of the chairs. That's a good negative cue. So here's a very clear example where you walk a longer distance because you had this positive pathway versus the negative pathway. And that's exactly what goes on when these cells move. You've got basement membranes, collagen fibers, and so forth, allow the cells in a positive way, and you've got negative signals, both hormonally and barriers, that keep it from straying on this path. And that's why during development, in the normal situation, all the cells tend to move the same way, in the same path. So you have directional cues, both positive and negative. Okay, does everybody see that? It's not charges.
Okay.
This is negative cues. This is not a charge.
How do negative cues prevent exactly how they prevent them from straying?
As I just said, they can form a barrier. They can form, like in this case, the chairs. I mean, why don't you walk down the chairs to come to here? Because it's a negative barrier. You don't want to trip and fall. And I wouldn't make it past one row before I fall, for example. So it's a negative barrier. Also, you've got other kinds of hormonal signals going on and so forth. It could be a variety of biological cues. Okay? So there's a set pattern for what happens. And that's the last little bit to talk about some of these general mechanisms. So in other words, when these cells move, it's not random. That's important to think about. So the last little part of this I want to talk about are inductive signals, which are hormone and hormone-like signals in development that change properties and shape and so forth. So inductive signals. And I want to give you a generic version first before I give you some examples. So let's consider the generic version. You got 2 round cells next to each other. Then you have these inductive signals are both positive and negative signals. Okay? In other words, regulation could go for a process or against the process, depending on what the process is. So let's consider the generic point of view. Two circles, two cells. You have a positive signal, and as a result, one of the cells becomes a square. So to get a square cell, you need the presence of the positive signal. Did everybody see that? Pretty straightforward, right? In contrast, you can get to the same point through a negative signal inhibiting a positive signal. And that is, say you have two cells in circles that require a positive signal to stay round. You then give it a negative signal, and now what happens is that positive signal is inhibited by this negative signal, and the neighboring cell becomes square. Same result, but here it's the absence of a positive signal gives you the square cell. So the inhibitory signal prevents this guy from working, so it becomes square. In both cases, in this generic point of view, you get a square cell, right? But in one case, it's due to having a signal that dictates that. In the other case, it's preventing some signal from keeping it round, so therefore it becomes square. Mechanistically, they're quite distinct, but the end result is the same, and both really are going on. I'll give you a very clear example of that in a second. Any questions on conceptually the difference here between a positive and negative signal? So a positive signal keeps things in a certain way. Negative signal tends to prevent a positive signal from working. Okay, yes? Can be. They can be across an entire embryo, for example. Where the signal's coming from. They tend to be in between from cells. Sometimes you can have a positive signal over there that's produced and a negative signal over there, and they come in together. And depending on the relative concentrations, one wins out over the other. That's the example I'm going to give you. Okay? All right. So let's talk about a specific example. And that has to do with where this has been studied a lot is the issue of polarity. I know you guys have been studying this in the lab a little bit. And here's an embryo. Obviously, from the structure, it's not a human embryo. It's probably some sort of frog embryo of some sort. And there's polarity. You've got a posterior end, an anterior end. You've got a left side, a right side, and importantly, you have a ventral, which is the underneath belly, and you've got a dorsal, which is the back. So you've got 6 points, the form of 3 dimensions. Okay, and one of these positive and negative signals I was talking about controls ventral versus dorsal polarity. So that's what we're talking about, back versus belly. So the ventral signal is BMP4, which is bone morphogenic protein 4. That's why these names of proteins that they originally founded by bone morphogenesis, but there's a whole family of them with a lot of different effects. BMP4 binds to receptor, which gives you ventral structures. Okay? So this is the positive signal. In the presence of BMP4, you get belly or ventral structures. Now, this particular system has an inhibitor to this. So if you put noggin into this mixture, what you get is dorsal structures. So as you can see from the polarity, ventral and dorsal are kind of opposite each other. So how does this work? Well, noggin is a negative signal, and BMP4 is the positive signal. And how this works is as follows. It's really an antagonist, but it works a little differently than what we've been talking about slightly. What happens is BMP4 is bound by noggin directly, which prevents BMP4 from going to the receptor, which prevents the ventral structures, and therefore everybody becomes dorsal. So what noggin is doing is directly binding to BMP4, preventing it from binding to its receptor, and therefore instead of ventral, you get dorsal. Everybody see that? So it's a form of an antagonist. Before we called antagonist binding to the receptor, preventing the response. This is another way in which it can work, an antagonist. It can bind to the actual signal or hormone-like molecule, prevent it from interacting with the receptor, and then preventing the response. In this case, preventing the ventral response mediates a dorsal response. Does everybody see that? And then in the embryo, which relates to one of the questions, is where these things come from, is that in the embryos, some of the slightly later structures, here's the embryo, here's the production of noggin from this side, and here's the production of BMP4 from this side. And these guys sweep in from either side of this. And so if you look at the concentrations, I put it right here, here's the concentration of noggin, and I'll make this a flatter cell, because here's the concentration of BMP4. So here the concentration of BMP4 is what? Much greater than noggin, right? Here it's greater, but not as much. Everybody see that? At this part, it's what, about 50-50? And here what? Noggin is greater than BMP4, and here there's almost all noggin. Everybody see that? So in this embryo, when noggin concentration is greater than BMP4, you get a dorsal structure because the inhibition wins out. But in the places where the noggin concentration is less than BMP4, which is down here, what do you get? You get ventral. So it's a matter of the stoichiometry. So here's roughly the boundary. Here, noggin is greater than BMP4, you get dorsal. Here, noggin is less than BMP4, and you get ventral. Does everybody see that? So in other words, going back to these inductive signals, when you have more positive signal, you get that response. When you have more negative signal, you get that response. Okay? This is just one example, but the big chunk of development is all based on relative concentrations of a signal at a given point in time. It's important to remember in development, during time, these signals can change in concentration. This is just one snapshot. Yes, question up there. When the concentrations are equal, very good question. It's the boundary between ventral and dorsal. That's all. Now, there are other signals that come in. I'm just giving you one snapshot of 2 signals, one negative, one positive, and others that play a role here. But it just forms the boundary. Very good point. Very good question. Yes, question. Is the dorsal side, again, I don't know the answer to that question. I'll look that one up too. Okay? I don't even know if there's any endometrium at that point in time in development, very frankly. But I will check it out. That's the important point is not so much what's attached to what. The important point is the relative concentrations of these signals dictate what the final structure is going to be. It's as simple as stoichiometry. So stoichiometry is a good thing. Okay? Those of us that had that in chemistry. Yes, Kristen. Say it louder, please. Again, I don't know the answer to that question. Is it radar? I'm not a developmental biologist. The lab, I'm sure, has some of those answers. The only thing I want you to know what's important from my point of view is, I mentioned radial ones work to have a similar mechanism, very frankly, is that hormone-like signals, the relative concentrations, are controlling the final structures. That is the important issue here. And all working through receptor-dependent processes. I can find out, because I imagine whatever my answer would be, it would change depending on the point in development. That's the other thing to remember. You have a time. You have a unit of time that's important. Yes, Alex? Yeah, very good point. Can you make it have two vector sides? What would happen if you took out the source of noggin and you put the source of BMP4 in there? What do you think what would happen? It'd be all belly. Some would say as we get older, that's what we are anyway, right? But yes, you can do those experiments. Also, you can add noggin to this side. And what would your prediction be? You get an extra dorsal. In fact, you get an embryo, a frog embryo. If you had source of noggin over here, you get something that looks like that, which has two dorsal sides and virtually no ventral. You can absolutely do those experiments, and those are the proofs that these are the molecules that control that process. Okay, one more before you go on? Todd, right?
Yeah.
Okay.
So if you didn't have noggin, but you only had BMP4 producing pressure on one side, with the smaller concentration of BMP4 on the other side, that causes like
Yeah, eventually, yeah. So if you had no noggin but BMP4, what would happen over here? Yes, you still get dorsal-like structure, ventral-like structures. You end up, I think, at the embryo, whereas this is two noggins. Without noggin, you get something that looks like that. That's all belly. Okay, so yeah, they've done those experiments, and you get the predicted answers if it's just the relative concentrations of these two molecules. They've absolutely done those. Yes. Now, one other one I want to talk about just briefly is limb buds, and I can put it up here. I'll actually leave it up here. It's polarizing in a limb bud. This is done in mice. Yes. I forgot what I deleted here. Right, the polarity. Okay. No, excuse me, good question. As you migrate from this side to this side, the concentration becomes less because you're farther away from the source. Whereas here, as the concentration of noggin migrates from this side to this side, the concentration is less. Just physically, it's less. Okay? Yes, that's true. And if you were in a technical relation, we never talk about this in office hours, but where noggin is greater than BMP4, you get dorsal. Where noggin is less than BMP4, you get ventral. That's what I want you to think about. Okay, last question by email. You can take it further. I'll be happy to answer it. Okay, so you have something called a limb bud, and you give it something called a ZPA, which is zone of polarizing activity. You get what's called posterior digits. And the way to think about that is, you can put your hand out like this, right? In this orientation. Where are these four? I know the thumb is up, but the four fingers are interior or posterior? They're downward, right? So they're posterior. So you're talking about the four digits and not the thumb. Those are your posterior digits. Don't go like this. Go like this. Straight out like that. Right? These are posterior digits. So in the zone of polarizing activity, you get your thumb and your posterior digits. This is done in a mouse. But as a further proof that ZPA is a positive signal, you can take another limb bud and you have your regular zone of polarizing activity. And it induces some genes that are not important at this point. You can add an extra zone of polarizing activity. What would you predict if you added a positive signal that gives you posterior digits? What would you predict? You get more posterior digits. And you end up with a claw in this case, or a paw, with extra posterior digits on both sides of the hand. So it looks like that. And that shows, and if you take away the ZPA, guess what? You don't get any posterior digits. So the point is you can show that these signals are actually acting on a pathway that induce the digits in this case. But there's many examples. I've just given you two examples. Yes? Oh, does this happen in nature? Parts of it happen in nature. There are humans out there that have 6 fingers, right? And it's thought that the genes that are downstream of the human equivalent of this creates an extra digit for exactly the reason. It's a positive signal. So that's why all you have to do is have some change where you get an extra signal and you get that extra finger. There's some baseball player I think has six fingers and he has special gloves that he uses for that. Okay, back there. But there are examples of that. It's actually a dominant gene. So if it stays in a small population, you get a lot of people with 6 fingers. Yes? These are the posterior digits. The thumb is an anterior digit. Yeah, so in the case of moving a second ZPA, the whole thing, you get something that looks like this. Right? The point is it shows that this is what's controlling that particular change. Okay, it's a dominant acting signal, which acts through receptors at some point. Was there another question somewhere? Yes, one last one. Can you form orbital thumbs? Yes, you can do all that. So for your budding science fiction writers, here's the beginning of designing the world's greatest guitar player, for example. Okay, any manipulation using fingers, you in theory can do this. You can certainly do it with mice. Obviously, there's ethical issues in humans, but yes, it works. And I assume if it works in mice, it'll work in humans experimentally.
Is this done by adding multiple layers?
In this case, this is done by adding this positive signal. ZPA is a positive signal. Okay. All right. So let's move on to systems. Beginnings of our systems flyby. Again, you cannot do physiology in 4 lectures, and the theme there'll be 2 themes. One will be, besides discussing some of the functionalities, capillaries and hormones. And if you know that, you know systems. The reason is, let's think about the systems we're going to talk about. We're going to talk about digestion. We're going to talk about a little bit about circulation.